January 5th, 1943, 06:30 hours, waters off Cape Hunter, Guadalcanal. Lieutenant Red Cochrane gripped the firing controls of his aft 5-inch battery aboard the light cruiser USS Helena, watching 4 Japanese Val dive bombers recede into the pre-dawn darkness after completing their attack run. Standard procedure dictated letting them go. At that range, with those angles, traditional anti-aircraft fire was mathematically futile, but Lieutenant Cochrane's guns were loaded with something the Japanese had never encountered, something so secret that most American commanders didn't know it existed. Shells marked with the cryptic designation Mark 32, containing miniaturized radio transmitters that would transform anti-aircraft gunnery from an exercise in statistical desperation into precision killing. He fired 3 salvos. 2 shells exploded within 70 feet of the lead Val without ever touching it. The dive bomber disintegrated mid-flight, torn apart by supersonic fragments from shells that had calculated their own lethal proximity, using technology Japanese engineers would have declared impossible. The other Vals scattered and fled. Lieutenant Cochrane's gunners had just demonstrated the future of aerial warfare, a future where gunners would no longer waste precious seconds, calculating lead angles, elevation corrections, or time-to-target estimates. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The shells themselves would think. This was the proximity fuse, a device so revolutionary that Secretary of the Navy James Forrestal would later declare it helped blaze the trail to Japan. Admiral Lewis Strauss ranked it among the handful of developments upon which victory very largely depended. Yet, unlike radar or the atomic bomb, the proximity fuse remained almost entirely unknown to the enemy forces it was killing. German and Japanese pilots died without understanding why American anti-aircraft fire had suddenly become devastatingly accurate. Their commanders, examining wreckage and interviewing survivors, could only conclude that American gunners had somehow achieved superhuman skill. The truth was more profound. American scientists had solved a problem that every major power had concluded was impossible. They had miniaturized complex electronics, hardened delicate vacuum tubes to survive artillery forces, and manufactured the result by the tens of millions. They had eliminated human error from the firing equation by putting intelligence into the ammunition itself. The mathematics of aerial combat, unchanged since the First World War, had been rewritten by American engineering. To understand the magnitude of this achievement, one must first understand the desperate inefficiency that preceded it. In the early weeks of the Blitz, British anti-aircraft batteries fired approximately 20,000 shells to bring down a single German aircraft. 20,000 rounds of high explosive, representing thousands of man-hours of manufacturing, tons of scarce materials, and countless moments of danger for the gunners below, all to achieve what amounted to random chance hitting a small, maneuvering target travelling at 300 miles per hour. The problem was straightforward to state, but seemingly impossible to solve. Aircraft moved in 3 dimensions at high speed. Anti-aircraft shells travelled in ballistic arcs, subject to wind, temperature, and the inevitable variability of manufacturing tolerances. A gunner had to predict where the aircraft would be several seconds in the future, calculate the ballistic path required to reach that point, set a mechanical time fuse to detonate at the correct altitude, and fire before the target changed course. Every variable introduced error. Wind speed estimates could be wrong. The aircraft could accelerate or turn. The time fuse mechanism might be slightly slow or fast. The gunpowder charge might burn inconsistently. Temperature affected shell velocity. Even if everything was perfect, the shell had to detonate within approximately 100 feet of the target to have any chance of inflicting damage. At engagement ranges of 20,000 feet, this meant achieving accuracy measured in tenths of a percent. Before the war, 2 types of fuses existed, both inadequate for the age of aerial warfare. Impact fuses, sometimes called crush fuses, detonated on physical contact with the target. This required actually hitting a maneuvering aircraft with a shell, a feat of such improbability that gunners joked about buying lottery tickets with better odds. The alternative was the time fuse, a purely mechanical device that used clockwork mechanisms to trigger detonation after a predetermined interval. Time fuses introduced their own cascade of complications. The fuse had to be set manually before firing, based on calculations performed by the fire control team. These calculations required knowing the target's current altitude, speed, heading, and rate of climb or descent. Even with optical rangefinders and mechanical computers, errors accumulated. A half-second mistake in fuse setting meant the shell exploded hundreds of feet from its intended detonation point, harmlessly dispersing fragments into empty air while the target flew unscathed through the space where it should have been. The human element compounded these technical limitations. Under combat conditions, with aircraft attacking at multiple altitudes and vectors, fire control teams worked in organized chaos. Range estimates had to be shouted to fuse setters. Fuse setters had to manually adjust each shell before loading. Loaders had to get each prepared shell into the gun quickly before the target moved enough to invalidate the calculation. The entire process, from target identification to firing, consumed precious seconds during which the tactical situation evolved. German Luftwaffe commanders understood these limitations intimately. They developed tactics specifically designed to exploit anti-aircraft inefficiency. High-speed approaches forced rapid recalculation. Multiple aircraft attacking from different altitudes overwhelmed fire control capacity. Jinking maneuvers at irregular intervals ensured that any calculated firing solution would be obsolete before the shell arrived. The result was psychological as much as tactical. Pilots learned that flying through anti-aircraft fire was frightening but statistically survivable. The sky would fill with black bursts of shrapnel, but most aircraft returned intact. American and British naval forces faced an even more acute version of this problem. Ships had finite ammunition storage. A carrier task force on extended operations in the Pacific could not afford to fire thousands of rounds at each attacking aircraft. Yet without effective anti-aircraft defense, ships were vulnerable to even obsolete aircraft like the Japanese Val dive bomber. A single hit from a 250-kilogram bomb could cripple a cruiser or sink a destroyer. The strategic implications were severe. Without reliable anti-aircraft defense, naval operations required continuous fighter cover, which limited operational range and duration. Amphibious landings became nightmares of vulnerability, with transport ships helpless against even modest air attacks. The entire architecture of naval warfare, built around aircraft carriers projecting power across vast distances, depended on solving the anti-aircraft problem. This desperation drove the search for alternatives. The concept of a proximity fuse was not new. Inventors and military planners had imagined such devices for decades. A shell that could detect its own proximity to a target and automatically detonate would transform anti-aircraft gunnery from educated guesswork into reliable killing. But imagination and engineering are different challenges. Every attempt to actually build such a device had failed for the same fundamental reasons. Germany had explored proximity fuses as early as 1930, developing over 30 different designs. Acoustic sensors were attempted, designed to trigger on engine noise. Electrostatic detectors were tested, intended to respond to the charged surfaces of aircraft moving through the atmosphere. Photoelectric systems were conceived, using light sensors to detect the target's silhouette. By 1939, German researchers had concluded that all approaches faced insurmountable technical obstacles. The fundamental problem was miniaturization. Any sensor system required electrical power, signal processing, and a reliable triggering mechanism. In the technology of the 1930s, this meant vacuum tubes, batteries, and complex circuitry. The smallest vacuum tubes available were those used in hearing aids, roughly the size of a pencil eraser. These delicate glass envelopes contained thin filaments and fragile internal structures, never designed for anything more violent than sitting in someone's pocket. An artillery shell experienced forces that would liquefy human tissue. When fired from a 5-inch naval gun, the shell accelerated from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This created acceleration forces of 20,000 times the force of Earth's gravity. A vacuum tube subjected to this violence would shatter instantly. The glass envelope would crack, the internal filaments would snap, the microscopic tolerances required for the tube to function would be obliterated in milliseconds. Even if the tubes somehow survived firing, they then had to endure the shell's rotation. Rifling in the gun barrel imparted spin for stability, rotating the shell at up to 25,000 revolutions per minute. The centrifugal forces were catastrophic for any delicate mechanism. Finally, after surviving this violence, the electronics had to function perfectly during the few seconds of flight time, operating in extreme temperatures, subject to vibration, and the aerodynamic stresses of supersonic flight. German engineers, working with some of the world's most advanced industrial capabilities, could not solve these problems. Hitler's leadership issued directives in 1940, prioritizing only projects that could reach production within 6 months to support the coming invasion of the Soviet Union. Germany's proximity fuse programs were shelved, though Rheinmetall-Borsig would resume limited work in 1944, far too late to affect the war's outcome. The British had reached further. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a miniature Doppler radar system. The concept was elegant. A small transmitter in the shell would emit radio waves. As these waves reflected off the target and returned to the shell, the Doppler effect would shift their frequency based on the relative velocity between shell and target. When the reflected signal reached a specific frequency indicating optimal detonation range, the fuse would trigger. British scientists tested prototypes on unrotated projectiles, essentially rockets, which experienced far less violent acceleration than gun-fired shells. They achieved promising results under laboratory conditions, but Britain's program was stymied by 2 critical obstacles that would prove decisive in determining who actually fielded a working proximity fuse. The first obstacle was cost. Britain's industrial capacity was already stretched to breaking by 1941. Fighter production, tank manufacturing, naval construction, and the countless other demands of total war consumed every available resource. The proximity fuse program required massive investment in new production facilities, specialized components, and quality control systems that didn't yet exist. British industry, besieged and partially destroyed by German bombing, simply lacked the spare capacity. The second obstacle was more fundamental. British engineers could not solve the miniaturization problem at the scale required for artillery shells. They developed working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was catastrophically inadequate. A 50% failure rate meant that half of all shells fired would be conventional time-fused ammunition subject to all the old inaccuracies. The tactical advantage would be minimal, nowhere near enough to justify the enormous investment. In September 1940, the British Tizard mission travelled to the United States as part of a broader technology exchange program. British representatives shared their research on radar, jet engines, and dozens of other advanced technologies with American scientists and military officials. Among these shared secrets was the concept of the proximity fuse, complete with circuit diagrams, test results, and the accumulated knowledge of British attempts to solve the problem. The Americans received this information at a moment of unique technological and industrial convergence. The National Defense Research Committee had been formed on June 27, 1940, bringing together leading American physicists and engineers under the direction of Vannevar Bush. The committee's explicit mission was to mobilize American scientific talent for war research before the United States formally entered the conflict. Merle Tuve, a physicist at the Carnegie Institution's Department of Terrestrial Magnetism, was assigned to lead the proximity fuse project. Tuve brought a brilliant but volatile temperament that would prove essential to driving the program forward. He understood immediately that British research had proven the concept, but failed at implementation. The Americans would have to start not from the British ending point, but from first principles, redesigning every component for manufacturability rather than mere functionality. What the British called Section T moved to newly established facilities at Johns Hopkins University's Applied Physics Laboratory in Silver Spring, Maryland. The laboratory began operations on March 10, 1942, in a rented Chevrolet garage, a modest beginning for what would become one of the most important weapons development programs of the war. Fuzes' team eventually numbered over 1,000 scientists, engineers, and technicians, all working under conditions of absolute secrecy on a device that most of them understood only in pieces. The team settled on a radio-based proximity fuse using Doppler radar principles similar to the British concept, but with crucial American modifications. A miniature transmitter in the nose of the shell would emit continuous radio waves at approximately 180 to 220 MHz. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect. The magnitude of this shift indicated range and closing velocity. When the reflected signal reached a predetermined threshold, indicating the target was within the shell's lethal radius of approximately 70 feet, an electrical circuit would close and detonate the explosive charge. The theory was elegant. Making it work required solving engineering problems that had never been attempted at this scale. Consider the constraints. The complete fuse assembly had to fit into the nose of a 5-inch artillery shell, occupying a space roughly the size of a wine bottle. Inside this limited volume, engineers had to fit a radio transmitter, a receiver circuit, a power source, amplification stages, safety mechanisms to prevent premature detonation, and the firing circuit itself. Every component had to survive storage for months in tropical humidity or Arctic cold, function reliably across temperature extremes from -40 to +120 degrees Fahrenheit, and most challenging of all, endure the 20,000 G acceleration of gun firing. For reference, a modern fighter pilot experiencing 9 Gs risks losing consciousness. The proximity fuse had to survive forces 2,200 times greater while maintaining the precise tolerances required for radio frequency operation. James Van Allen, a young physicist who would later discover Earth's radiation belts, joined the Applied Physics Laboratory in April 1942 as a founding member. He faced the task of developing what the team euphemistically called rugged vacuum tubes. He started with miniature tubes that Raytheon and Sylvania had developed for hearing aids, examining them under microscopes to understand their construction and failure modes. Van Allen established a brutal testing regime. Tubes were mounted in metal blocks and subjected to rifle fire from .22 caliber weapons to simulate shock loading. They were placed in lead containers and dropped from buildings to test impact resistance. Most dramatically, complete fuse assemblies were fired from a vertical gun into the soft earth at the Naval Proving Grounds in Dahlgren, Virginia. The earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under magnification to document exactly how and why they had failed. Working with Sylvania Company engineers, Van Allen redesigned the vacuum tubes from first principles. The glass envelopes were thickened and carefully annealed to increase strength. The internal filaments and grid structures were redesigned with shorter spans and heavier cross-sections to resist the crushing forces of acceleration. The mounting systems were completely rethought. Instead of simple socket connections, the tubes were potted in wax inside the fuse body, which cushioned them against shock and vibration. Through hundreds of test firings and thousands of design iterations, reliability gradually improved. By September 1941, success rates climbed above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up, and they were proven correct. By early 1943, reliability had climbed above 90%. But vacuum tubes were only one challenge among dozens that had to be solved simultaneously. The power problem required particular ingenuity. Batteries of the era were either too large to fit in the fuse housing or too weak to power the radio circuit for the required duration. Chemical batteries also had severe limitations in shelf life and temperature tolerance. The solution was a tiny wind-driven generator that activated only after the shell left the gun barrel. A small propeller, protected during firing by a safety cap, would extend into the slipstream once the shell was airborne. The airflow spinning the propeller at high speed generated electricity to charge capacitors that powered the radio circuit. This meant the fuse was completely inert until fired, eliminating any possibility of accidental detonation during handling or storage. It also meant the fuse was impossible to detect or jam until the final seconds of flight, when the shell was already committed to its trajectory. German and Japanese forces would eventually suspect that something electronic was involved in American anti-aircraft accuracy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But without working examples to examine, they could not determine operating frequencies or develop countermeasures. The manufacturing challenges were equally daunting. Each fuse contained approximately 130 components manufactured to tolerances of 1/10,000th of an inch. The radio oscillator circuits had to maintain frequency stability across temperature extremes and mechanical stress. The amplification stages required precise component values. The firing circuit had to be absolutely reliable, detonating when commanded but never prematurely. Quality control became an obsession. The Applied Physics Laboratory developed manufacturing standards and testing protocols that didn't exist in commercial electronics production. Clean rooms were established decades before the semiconductor industry would make them standard practice. Every component was tested multiple times before assembly. Complete fuses underwent functional checks and test firings before acceptance for combat use. By late 1943, American factories were producing 40,000 proximity fuses daily. This production rate would eventually reach 70,000 per day by war's end. The scale was staggering. More than 100 manufacturers across the United States contributed components. The Crosley Corporation alone employed over 10,000 workers producing fuses, hitting peak production rates of 16,000 units per day from a single facility. Women comprised much of the assembly workforce, performing precise electronic work that required steady hands and attention to detail that male workers often lacked. These women, many of whom had never worked in electronics before the war, pioneered assembly techniques that would become standard practice in the post-war electronics industry. They worked without knowing what they were building, told only that their work was vital to the war effort and subject to the highest security classification. The first combat test occurred on August 12, 1942. The newly commissioned light cruiser USS Cleveland, conducting its shakedown cruise in Chesapeake Bay, began a scheduled 2-day evaluation of the proximity fuse against radio-controlled target drones. The drones were sophisticated aircraft, difficult to hit under the best circumstances. Navy planners expected to expend dozens of shells over 2 days of testing to bring down all 3 targets. The Cleveland's gunners destroyed all 3 drones on the first day with just 4 shells. 2 drones were obliterated so completely that the test officers, who had never seen such thorough destruction of their expensive equipment, initially believed something had gone catastrophically wrong with the drones themselves. When the 3rd drone was brought down almost instantly the following morning, the Navy cancelled the remainder of the test. There was nothing left to prove. The proximity fuse worked beyond anyone's expectations. By the end of 1942, 5,000 rounds of proximity-fused ammunition had been shipped to the Southwest Pacific and distributed to select vessels. The Enterprise and Saratoga carriers received allocations, as did the light cruiser Helena. Security restrictions were absolute. Only ships operating in areas where dud shells would fall into deep water were authorized to use the ammunition. The risk of a fuse falling into enemy hands, where it could be reverse-engineered, was considered too severe to allow use over land or in shallow coastal waters. Lieutenant Red Cochrane's engagement on January 5, 1943, marked the first combat use. The Helena was returning to Guadalcanal after a night raid against Japanese airfields when 4 Val dive bombers attacked at dawn. The Vals were obsolete aircraft, slow and vulnerable, but their durability and the skill of their pilots made them dangerous. One Val scored a hit on the New Zealand cruiser Achilles before the group broke off its attack. As the Vals departed, the Helena's aft battery fired 3 salvos with proximity-fuzzed shells. The results exceeded even the optimistic predictions from the Chesapeake Bay tests. 2 shells exploded near enough to the lead Val to fatally damage it with shrapnel. The aircraft disintegrated mid-flight, a fate that no Japanese pilot had experienced from anti-aircraft fire at that range and angle. The other Vals scattered in confusion and fled at maximum speed. Samuel Eliot Morison, in his authoritative History of United States Naval Operations in World War II, wrote that the attackers did not escape with whole hides. Smoking fuselages and bright surface bonfires attested to the accuracy of anti-aircraft batteries and the efficiency of the super-secret Mark 32 shell fuse, which here had one of its first combat tests. That year, 1943, proximity-focused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, even though only 25% of shells fired had been fitted with VT fuses. The mathematics were revolutionary. Traditional time-focused shells required an average of 654 rounds to bring down a single aircraft in Pacific combat. Some estimates ranged as high as 20,000 rounds per kill under adverse conditions. Proximity-focused shells achieved kills with a 3-to-1 improvement over conventional ammunition, requiring approximately 200 rounds per aircraft destroyed. This meant ships could defend themselves with one-third the ammunition expenditure, extending operational range and reducing the logistical burden of resupply. More significantly, the fuse eliminated the human element from fire control calculations. Gunners no longer needed to estimate range, calculate lead angles, predict target maneuvers, or set mechanical time fuses. The shells calculated their own proximity to the target and detonated at optimal range automatically. This transformed anti-aircraft gunnery from a complex technical problem requiring split-second calculations under combat stress into a relatively simple task of pointing guns in the general direction of the target, firing. The psychological impact on enemy pilots was immediate and profound. Japanese aircrew had learned to ignore anti-aircraft fire as frightening but statistically survivable. The sky would fill with black puffs of shrapnel, and experienced pilots would fly through it with minimal concern. But proximity-focused fire was different. Shells exploded precisely at the aircraft's altitude, with uncanny accuracy. There was no safe corridor between the bursts. Evasive maneuvering provided no protection because the shells adjusted their detonation point based on actual target position. Japanese pilots began reporting to their commanders that American gunners had achieved superhuman skill. The idea that the shells themselves were intelligent was so far beyond Japanese technological expectations that it wasn't seriously considered until much later in the war. Japanese naval aviation, already suffering from the attrition of experienced pilots at Coral Sea and Midway, could not afford to lose aircraft to what appeared to be impossibly accurate anti-aircraft fire. The June 19th through 20th, 1944, Battle of the Philippine Sea demonstrated the proximity fuse's decisive impact on large-scale naval combat. Vice Admiral Jisaburo Ozawa commanded the Japanese mobile fleet with 9 carriers embarking approximately 430 aircraft. Land-based aircraft added another 540 planes theoretically available for the operation. Against this force, Vice Admiral Mark Mitcher's Task Force 58 deployed 15 aircraft carriers with 891 embarked aircraft. The Japanese plan relied on superior range. Japanese carrier aircraft could attack at 300 miles, while American Hellcats were limited to 200 miles. Ozawa intended to launch strikes beyond American counterattack range, using land-based aircraft to supplement carrier strength and compensate for numerical inferiority. The plan might have worked against conventional anti-aircraft defenses. It failed catastrophically against proximity-focused fire, combined with superior American radar and fighter direction. On the morning of June 19th, Japanese aircraft approached in 4 massive waves. American radar detected the formations at extreme range, providing ample time to prepare defenses. As Japanese aircraft closed, they encountered a coordinated defense that had been impossible to achieve with time-focused ammunition. Fighters were vectored to intercept using radar guidance. Those aircraft that penetrated the fighter screen faced anti-aircraft fire of unprecedented accuracy. The shells exploded at precisely the right altitude without requiring time fuse settings. Gunners could concentrate on tracking targets rather than calculating firing solutions. The sky filled with air bursts that appeared to track individual aircraft, detonating at optimal range regardless of altitude changes or evasive maneuvers. To the Japanese pilots, it seemed as if every shell was guided directly to its target. The aerial engagement became known as the Great Marianas Turkey Shoot. Naval aviation and anti-aircraft fire shot down nearly 480 Japanese aircraft. 346 of those were carrier aircraft destroyed on June 19 alone. American losses totaled fewer than 24 Hellcats in air-to-air combat. The battle eliminated the Imperial Japanese Navy's ability to conduct large-scale carrier operations. Japan would never again be able to challenge American naval aviation in fleet-scale combat. James Van Allen, one of the Proximity Fuze's primary developers, was present during the battle aboard the battleship USS Washington. He witnessed kamikaze attacks against American ships and saw proximity-fused shells detonating around incoming aircraft with lethal precision. He later described seeing at least 2 or 3 5-inch shell bursts in the vicinity of attacking planes, then watching the aircraft dive into the water several hundred yards short of their targets. The shells had wounded or killed the pilots or damaged control surfaces, rendering the aircraft unable to complete their attacks. The strategic implications extended far beyond individual engagements. American ships equipped with proximity-fused ammunition could operate with confidence in waters where Japanese air power remained active. Amphibious landings could proceed with reduced risk of catastrophic air attacks on vulnerable transport ships. Carrier task forces could extend their operational range, knowing that anti-aircraft defenses were reliable rather than merely hopeful. From December 1944 through the Allied crossing of the Rhine in March 1945, proximity-fused anti-aircraft fire destroyed more than 1,000 German aircraft. This occurred during a period when the Luftwaffe made desperate attempts to challenge Allied air superiority over Western Europe. German pilots, many of them inadequately trained replacements for losses suffered on the Eastern Front and in the Battle of Britain, faced anti-aircraft defenses that made low-level attacks suicidal and high-altitude operations ineffective. The defense of London against Vone flying bombs provided perhaps the most dramatic demonstration of the Fuze's effectiveness. The Vone was a pulse-jet-powered cruise missile, small, fast, and difficult to engage with conventional anti-aircraft fire. When the Vone campaign began in June 1944, British anti-aircraft batteries achieved a destruction rate of only 17%. The flying bombs were simply too small and too fast for time-fused shells to reliably intercept. Authorization for proximity-fused ammunition against V-1s was granted on June 12, 1944. British and American 90mm anti-aircraft guns were deployed along the English coast in a defensive belt specifically designed to maximize the use of VT-fused ammunition. The results were extraordinary. Within 4 weeks, the destruction rate climbed from 17% to 74%. On some days, the rate exceeded 80%. By the end of August, when Germany launched 104 V-1s in a final massive attack, 68 were destroyed by proximity-fused shells. Only 4 reached London. The strategic value of keeping Antwerp operational cannot be overstated. Antwerp was the largest port in Europe capable of supporting Allied logistics for the final drive into Germany. Without it, supplies would have to flow through more distant French ports, adding weeks to delivery times and constraining offensive operations. The proximity fuse, by defeating the Vone threat to Antwerp, effectively shortened the war by maintaining Allied supply lines at a critical moment. But the most revolutionary application of the proximity fuse remained forbidden through most of 1944. The Pentagon had categorically refused to authorize use of proximity-fused ammunition over land. The reasoning was sound from a security perspective. Artillery shells fired over water would either detonate or fall into the ocean, where recovery was nearly impossible. Shells fired over land might fail to detonate, providing the enemy with intact examples to examine, reverse engineer, and potentially copy. The fear was not merely that Germany or Japan might develop their own proximity fuses, though that would have been serious enough. The greater concern was that enemy engineers might identify the operating frequencies and develop jamming systems. A proximity fuse that could be reliably jammed would actually be worse than conventional ammunition because it would give commanders false confidence in their anti-aircraft defenses while providing no actual improvement in lethality. This changed on December 16, 1944. At 05:31 hours, German forces launched Operation Watch on the Rhine, Hitler's last desperate offensive in the West. The attack targeted the thinly held Ardennes sector, striking at the boundary between American army groups where defenses were weakest. Colonel Oscar Alfred Axelson of the U.S. 46th Artillery Group watched German forces massing in the pre-dawn darkness through his field glasses, knowing that the 38th Cavalry Squadron defending the northern shoulder would be overwhelmed without immediate artillery support. Axelson stared at the classified ammunition crates marked T-98, the designation for proximity-fused artillery rounds. Standing orders from Allied High Command explicitly forbade their use over land. But Axelson understood that the Germans were about to break through American lines, potentially reaching the critical supply port of Antwerp and threatening the entire Allied position in northwest Europe. Within 47 minutes of the German offensive commencing, Axelson made his decision. Load the VT shells. The shells that American artillery began firing at 06:18 hours contained the same miniaturized radio technology that had transformed naval anti-aircraft gunnery, but adapted for a fundamentally different purpose. Against aircraft, the fuse detected the metal surface of the target and detonated when within optimal range. Against ground forces, the fuse detected the Earth itself, detonating at precisely 30 feet above the surface, regardless of terrain variations. This seemingly minor distinction created catastrophic changes in artillery effectiveness. A conventional high-explosive shell detonating on contact with the ground sent 50% of its fragments into the earth, 45% outward in a horizontal pattern, and only 5% upward. A soldier in a properly constructed foxhole, dug to regulation depth with adequate overhead cover, had a 90% chance of surviving conventional artillery. The proximity fuse changed these mathematics with brutal finality. Detonating at 30 feet altitude, 100% of fragments traveled downward or outward in an inverted cone pattern. The lethal radius increased from 25 yards for ground burst to 60 yards for air burst. More critically, the fragments arrived at 30 to 45-degree angles, perfectly aligned to enter foxholes, trenches, and rifle pits. The lethal fragment area increased from 60 square feet with conventional fuses to 3,000 square feet, a 50-fold improvement that made traditional field fortifications largely ineffective. The effect on German forces attacking through the Ardennes was immediate and psychologically devastating. German infantry had survived years of conventional artillery bombardment on the Eastern Front. They understood how to construct defensive positions, how to time movements between barrages, how to survive in terrain that provided cover from horizontal fire. But they had no defense against shells that exploded directly overhead with surgical precision. The 99th Infantry Division's after-action report documented the results. VT-fused concentrations on German assembly areas near Krinkelt resulted in extraordinary casualties among lead battalions within 12 minutes of fire mission commencement. Enemy medical services were overwhelmed. Advancing units were forced to step over their own dead to continue the attack. By December 23rd, military intelligence estimated 2,000 German soldiers had been killed by proximity-fused rounds during the fighting around Malmö, where artillery battalions fired with great effect against SS forces. General George Patton wrote a letter to the War Department describing his experience with the new ammunition. "The new shell with the funny fuse is devastating," Patton wrote. "We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." German soldiers facing proximity-fused artillery experienced a fundamental collapse in their understanding of battlefield survival. Infantry doctrine, refined over centuries of warfare, taught that the earth provided protection. Dig deep enough, construct adequate overhead cover, and you could survive artillery bombardment. The proximity fuse rendered this wisdom obsolete in an instant. There was no depth sufficient to provide safety. Overhead cover that stopped conventional shell fragments was useless against airbursts. The only defense was dispersion, spreading forces so widely that a single shell could not catch multiple targets, but dispersion reduced combat effectiveness. German tactical doctrine had evolved around concentrated formations that could mass firepower and coordinate movements. Spreading units to counter proximity fuses weakened overall capability even as it reduced casualties. The final months of the war saw some German units essentially paralyzed by fear of American artillery. They would not move during daylight. They avoided any position that appeared to be a likely target. Morale plummeted as soldiers realized they had no defense against a weapon that turned their training and experience into liabilities. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender, not the fear of death, which soldiers had long accepted as part of combat, but the specific fear of proximity-focused artillery, which provided no chance of survival and no way to fight back. This was psychological warfare at its most effective, accomplished not through propaganda, but through demonstrated futility of resistance. The Germans captured an American ammunition dump during the Battle of the Bulge containing 20,000 proximity fuses for artillery shells. German engineers examined these devices with a mixture of astonishment and despair. They had concluded years earlier that miniaturized radio fuses were impossible because the acceleration forces of gun firing would destroy any electronic components. Faced with physical evidence that the Americans had solved this impossible problem, German scientists struggled to comprehend the scale of industrial and technical capability the fuses represented. Some German commanders offered rewards to any soldier who recovered an intact proximity fuse. The desperation was evident. German forces needed to understand how the fuses worked, what frequencies they used, whether jamming was possible. But recovery of intact fuses proved nearly futile. The devices were designed to detonate on impact if they failed to function properly in flight. Even when duds were recovered, the components were so thoroughly damaged by the impact that reverse engineering was impossible without working examples to compare against. What the Germans never understood was that the proximity fuse represented more than clever electronics. It represented a fundamental difference in how America and Germany approached weapons development. Germany invested heavily in advanced technologies that required years of development and could not be mass-produced in meaningful quantities. Jet aircraft, ballistic missiles, guided bombs, these were technological marvels that arrived too late and in too few numbers to affect the war's outcome. America invested in technologies that could be mass-produced immediately. The proximity fuse, while sophisticated, was designed from the start for manufacturability. Every decision in its development prioritized production volume and reliability over theoretical perfection. The result was a weapon available in overwhelming numbers when needed. By war's end, more than 22 million proximity fuses had been manufactured, 22 million sophisticated electronic devices, each containing miniaturized components built to impossible tolerances, produced in the span of 3 years by a nation that had barely begun war production when the project started. The scale of this achievement becomes clear when examining production statistics. Exactly 22,734,481 proximity fuses were manufactured between 1942 and 1945. Of these, 21,685,157 were shipped for combat use. Another 388,324 were consumed in testing. Each fuse required approximately 130 components manufactured to tolerances of 1/10,000th of an inch. The total represented more than 3 billion precision components assembled under cleanroom conditions by workers who often didn't know what they were building. This industrial achievement occurred simultaneously with every other demand of total war. America was building aircraft carriers, mass-producing tanks, manufacturing millions of rifles, constructing the atomic bomb, feeding Allied forces worldwide, and supporting the Soviet Union through Lend-Lease. The proximity fuse program competed for resources with dozens of other critical projects, yet still achieved production volumes that overwhelmed enemy capabilities. The fuse's impact on anti-aircraft gunnery specifically deserves examination of its strategic implications beyond individual engagements. Before proximity fuses, American naval forces required approximately 654 shells, to bring down a single aircraft. With proximity fuses, this dropped to approximately 310 shells per kill against kamikaze attacks and 624 shells against conventional attacks. This improvement in efficiency meant that ships could defend themselves with less than half the ammunition expenditure. Reduced ammunition consumption translated directly into extended operational range. Aircraft carriers could remain on station longer before requiring resupply. Amphibious operations could proceed with smaller logistics trains. The cumulative effect was that American naval forces could project power across vast distances of the Pacific without being constrained by anti-aircraft ammunition availability. This was the foundational capability that enabled the island-hopping campaign from Guadalcanal to Okinawa. The Battle of Okinawa in 1945 provided a final demonstration of the Fuse's life-saving capability. On May 11, 1945, the destroyers USS Hadley and USS Evans, along with 4 landing craft supply ships, faced a 90-minute suicide attack by 156 kamikaze aircraft. The small group of ships, armed extensively with proximity-fused ammunition, shot down dozens of attacking aircraft. Though both destroyers were eventually hit and damaged, they survived an attack that would have been catastrophic against ships armed with conventional ammunition. The Bureau of Naval Personnel Bulletin All Hands described the aftermath. The fighter director tally revealed that the little group of ships and planes had to oppose a total of 156 enemy planes. At the end of the first half hour, the Evans had been hit 4 times by suicide planes, each ablaze from anti-aircraft fire. The Hadley had knocked down a dozen enemy planes, and the Evans had accounted for 23 before she had to retire from the fight. Indispensable was the verdict on the role played by VT-fused ammunition in this action. The technological legacy of the proximity fuse extended far beyond World War II applications. The miniaturization techniques developed for the fuse influenced the entire post-war electronics industry. The quality control methods became standard practice in precision manufacturing. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training and supervision. These lessons shaped American industrial development throughout the Cold War era. The scientists and engineers who worked on the proximity fuse went on to distinguished careers that helped establish American technological leadership in the second half of the 20th century. James Van Allen became one of the founding figures of space science, discovering Earth's radiation belts using instruments carried aboard early satellites. Merle Tuve continued leading scientific research at the Carnegie Institution. Dozens of others joined universities, industrial laboratories, and government research facilities, bringing expertise in miniaturization, electronics, and systems engineering. The organizational lessons proved equally enduring. The proximity fuse program demonstrated that democratic societies could mobilize scientific and industrial resources as effectively as totalitarian states. The integration of academic research, industrial production, and military application became the model for Cold War weapons development. Programs like the Manhattan Project drew directly on organizational structures pioneered during proximity fuse development. The fundamental question the proximity fuse answered was whether American gunners could stop calculating lead, stop estimating range, stop setting mechanical time fuses, and simply fire shells that would think for themselves. The answer transformed aerial warfare. From January 5, 1943, when the Helena first fired proximity-fused shells in combat, until August 1945, when Japan surrendered, American gunners no longer needed to be mathematical geniuses under fire. They needed only to point their guns toward the target and fire. The shells calculated their own proximity using miniaturized radar. They detected targets using Doppler frequency shifts. They detonated automatically at optimal range. They eliminated human error from the firing equation by putting intelligence into the ammunition itself. American gunners stopped calculating lead because American engineers had built shells capable of calculating for themselves. Over 500 German aircraft destroyed by proximity-fused fire in Europe, nearly 500 Japanese aircraft downed at the Philippine Sea. 79% of Von flying bombs destroyed over London, 2,000. German soldiers killed in a single concentrated barrage at Malmi. These were not the results of superior gunnery skill. They were the results of superior technology deployed at overwhelming scale by an industrial democracy that solved impossible problems through the application of extraordinary resources, brilliant engineering, and a manufacturing base that treated technological miracles as production quotas. The proximity fuse represented everything that made American power decisive in World War II. It combined advanced science with practical engineering. It required massive investment but produced proportionate results. It was sophisticated yet manufacturable, effective yet affordable at scale, innovative yet reliable. It was developed by free scientists working in cooperation rather than competition, manufactured by workers who took pride in precision even when they didn't know the final application, and deployed by military forces who understood that technology multiplied the effectiveness of courage. When Lieutenant Red Cochrane fired those first 3 salvos off Guadalcanal, he inaugurated a new era in warfare, an era where ammunition itself contained intelligence, where shells calculated their own targeting solutions, where human gunners were liberated from impossible mathematical demands and could focus on the tactical employment of weapons rather than the mechanics of firing them. The proximity fuse didn't make gunners obsolete. It made them effective beyond anything previous generations of artillerymen had imagined possible. The German and Japanese forces who faced proximity-fused fire understood this implicitly. They were not defeated by superior courage or better tactics. They were defeated by an industrial and scientific establishment that had solved problems their own experts had declared impossible. They faced shells that exploded at precisely calculated altitudes, aircraft that fell from the sky without being directly hit, artillery barrages that turned foxholes into death traps. They faced the future, and the future was American. The proximity fuse stands as testament to what democratic societies can achieve when they combine scientific excellence with industrial might and unwavering determination. Over 500 German planes shredded from the sky, countless lives saved by technology that transformed near misses into kills. American gunners who stopped calculating lead because American engineers had built something better than human calculation. A shell that knew when to explode, a fuse that thought for itself, a weapon that changed warfare by making the impossible routine. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.